Section 3.4, Transformations of Cubic and Quartic Functions. The learning goals of today's lessons are to describe the transformations performed on cubic and quartic functions given in an equation, to simplify the transformations to eliminate horizontal stretches and compressions, use mapping notation to graph a transformed cubic or quartic, and derive an equation of a cubic or quartic given the graph. So in general, transformations on a cubic or quartic are the same as transformations seen previously. So we have our A, our horizontal stretch factor, our horizontal compression factor, K, or horizontal stretch factor, depending on what it is, D, our horizontal shift, and C, our vertical shift, and the same applies for a quartic as well. In general, the general form for polynomial functions is this, right, where n is an element of natural numbers. So natural numbers being numbers starting at 1, right? So, 1, 2, 3, 4, not including 0 in this case. So example 1 is fairly straightforward. It says describe the transformations performed on the cubic function to graph y is equal to -8, bracket 1/2 x plus 1, all to the power of 3 minus 3. So what we're going to do here is hopefully you immediately notice that this graph, or rather this function, needs to be factored in order to accurately determine the horizontal shift factor. So what I'm going to do is I'm going to start by factoring this. So y is equal to -8, bracket 1/2, factor out the 1/2, x, then plus 2. All of that is cubed, then minus 3. So recall that we have to talk about our transformations in RST order, or SRT order, which is to say reflections and stretches first, because they pertain to multiplication, and then your translations left and right and up and down, because those pertain to addition and subtraction, right? So your multiplications come before addition and subtraction in order of operation, so your reflections and stretches come first. All right, so the first thing that we have right here is we have a reflection in the x-axis. So reflection in the x-axis. So that's the negative right there. Then we have an 8, so we have a vertical stretch by a factor of 8. And then our k value is 1/2, so that correlates to a horizontal stretch by a factor of 2. As always, we recall that our k value, we take the reciprocal of the k value to determine the stretch factor. So horizontal stretch by a factor of 2. Okay, and then we have a horizontal translation. Sorry, not 8, but rather 2 units. Two units left. And we have a vertical shift, or vertical translation, 3 units down. We can eliminate these horizontal stretches and compressions by incorporating them into the vertical stretch factor. So let me show you how that's done. Cubic and quartic functions, as well as quadratic and quintic, can be simplified to eliminate the horizontal stretch factor k. So let's take a look. Consider the above function, y is equal to -8 times 1/2 x plus 1 cubed minus 3. So this is the one that we just looked at. Use exponent rules to simplify this function and verify using a graphing app to determine if it produces the same function. All right, so what we can do here is we can take a look at this right here. So that's y is equal to -8 1/2 x plus 1 cubed minus 3. As I did previously, I'm going to factor out that 1/2, and then I have x plus 2 cubed minus 3. So the goal here is to get rid of this horizontal stretch factor. So I, in fact, can use my exponent rules because I have two factors here being multiplied, right? The 1/2 multiplies the x plus 2. This exponent can be applied to the 1/2, and it can also be applied to the x plus 2. This correlates to this exponent law, which is that if you have a times b to any exponent, let's just say for in this case is a times b to the power of 3, well, that just equals a cubed times b cubed, right? Again, these two factors here have to be multiplying, right? A times b. So what we're going to do here is we're going to apply that cube to the 1/2. So we end up with y is equal to 8, and then 1/2 cubed. And we still have our cubic because we have x plus 2 cubed minus 3. When we have an exponent outside of fraction, well, that means that the exponent applies to the numerator and the exponent applies to the denominator. So I'll go ahead and just show that in a different color. So that 3 applies to the exponent, 3 applies to the 1, and it applies to the 2. And we end up with 8 times, and that's 1 cubed, well, that's still 1, over 2 cubed, well, that's 8. And then x plus 2 cubed minus 3, and y is equal to, well, 8 times 1 over 8, that's just 1, x plus 2 cubed minus 3. If you were to graph this right here in Desmos, and you were to graph this right here in Desmos, you would obtain the exact same graph. So what we have done is we eliminated the 1/2 stretch factor by incorporating it into the vertical stretch factor, and then having incorporated it into the vertical stretch factor, we actually eliminated both. So we really simplified what we had to begin with. So as I said, this right here produces the exact same graph as this right here. So use mapping notation to sketch the graph of y is equal to negative bracket x plus 2 cubed minus 3. All right, so what we're going to do is, if we use mapping notation, we have y is equal to x cubed, that's our parent function, x and y. And then if we were to take a look at this, we have y is equal to negative x plus 2 cubed minus 3. Well, what that is that is a horizontal shift 2 units to the left. All right. And then we have a reflection in the x-axis, so negative y, and then we have 3 units down, minus 3. We're going to pick a few points here that are, fairly common for our cubic function, right? And so that would be like, for example, negative 2 gives us negative 8, negative 1 gives us negative 1, 0, 0, 1, 1, and 2, 8. These are all points on the parent function y is equal to x cubed. Now we're going to have to translate these into our transformed function. So we have negative 2 minus 2. Negative 2 minus 2 is negative 4. Negative 8 times negative 1, that's 8, minus 3 is 5. And then we have negative 1 minus 2 is, that's negative 3. And then negative 1 times negative 1, so my negative 1 here times negative 1, that's positive 1 minus 3, well, that's negative 2. And then 0, 0 gets transformed into negative 2 and negative 3. 1, 1 would get transformed into negative 1, and 1 times negative 1 is negative 1, minus 3 is negative 4. And then over here we have 2, 8, so 2 minus 2 is 0. And then negative 8 minus 3, well, that's negative 11. Okay, so I'm just going to pause this now while I plot these points and sketch the graph. Okay, so I've gone ahead and sketched the graph here, and again, it's not the best graph sketching. I think that's just a product of the tools that I'm using for my digital lesson delivery, but effectively this should make sense because we have a cubic function that has shifted left by 2 and down 3, so left by 2, down 3. And then it's also been reflected in the x-axis. And this should also stick out to you as well. It has a negative leading coefficient, which means that it's got to go from the second quadrant to the fourth quadrant. And so that should make sense. All right, what we're going to do is we're going to move now to determining the equation of a cubic or a quartic from a graph. There are several ways to go about this. However, an easy way is to start with the horizontal and vertical translations, then sub a point to find the vertical stretch factor. So note, this will provide the simplified form in which the horizontal stretch has been eliminated. I actually think this is probably the easiest way to go about this. So again, you find the vertical and horizontal translations by determining where 0, 0 on the original parent function has been moved to, and then you find your stretch factor. So if I take a look at the first one, it says determine the equation of the following graph. So I have a quartic graph here, right? And note that the quartic graph typically starts at 0, 0. So it looks like it's been shifted right 4 units and shifted up 1 unit. Well, that already gives me a fair amount of information. So I'll go ahead and write the general form first. Y is equal to A, x minus d to the power of 4 plus c. And then I see that I don't know what my stretch factor is just yet, but I know that it's been shifted over 4 units, so x minus 4. And then it's been shifted up 1 unit. This graph conveniently provides me a couple of extra points I can use, and it really doesn't matter which point you do choose to use. I'm just going to use 5, 2. So when x is equal to 5, that produces a y value of 2. So therefore, I'm going to sub x and y as 5 and 2 into the above equation. So my y value is going to be 2. 2 is equal to a. My x value is going to be 5. 5 minus 4 to the power of 4 plus 1. And that should help me isolate and solve for a. 2 is equal to a, and 5 minus 4 is 1 to the power of 4 plus 1. Well, 1 to the power of 4 is just still 1, so I have a plus 1. And then subtracting 1 from both sides, I'll get 1 is equal to a. So I have my vertical stretch factor, and my final answer is y is equal to, and a is equal to 1, so I'm not going to bother with that, x minus 4 to the power of 4 plus 1. So that's the equation of the quartic you see above. Same thing with this as well. What I'm going to do here is normally my cubic graph goes through 0, 0. I see it's been shifted over to the right 1 and up 1. So I'll write my general equation for a transformed cubic, which is this. And then I will insert my shifts, which is y is equal to a, x minus 1 cubed plus 1. I'm going to sub one of these points in, so I'll sub, for x and y, I will sub, let's say, 0, 3. I'll sub in my y-intercept, right? 0 and 3. So y is equal to 3 when x is equal to 0, so 0 minus 1 cubed plus 1. 3 is equal to a times negative 1 cubed plus 1. Well, negative 1 cubed is still negative 1. So negative 1 times a is just negative a plus 1. Okay. Let's isolate and get a by itself. So I'll bring the 1 over to the other side. Subtracting 1 from both sides, that gives me 2. 2 is equal to negative a, and therefore a is equal to negative 2. So then I go ahead and I'll write my equation, which is y is equal to negative 2 x minus 1 cubed plus 1. Again, this seems to make sense because we have a negative stretch factor, right, or negative leading coefficient. And as I can see, my cubic goes from the second quadrant to the fourth quadrant. So yeah, this definitely seems to make sense. Homework is listed here on the bottom. Thanks for watching.